to be here with Siobhan, and I'll share my PowerPoint. So today I'm going to be talking to you about the biliary enterohepatic circulation and estrogen dominance. So let's get an overview of the digestive system. Really, the process of digestion begins in the mouth and with our senses and our sense of smell. When you hear your favorite kind of food being mentioned, or when you have the smells of your favorite food cooking in the kitchen, you automatically start salivating. And that's the first step to our whole digestive process. And when we chew our food and the saliva and the muscles of the tongue that mix it all up with the ptyalin in the saliva, that's where digestive process begins and food gets masticated and broken down, initially in the mouth itself, from complex carbs into a few simple carbs. And then, of course, it travels down the food pipe or the esophagus to enter into your stomach. And in the stomach itself, it is the HCl, or the stomach acid, that helps us break down especially our proteins in our meals. And then it goes into the duodenum, which is a very, very significant part of the whole digestive tract and the digestive process, because here is where the common bile duct from the gallbladder and the liver enters the duodenum and secretes bile, along with the pancreas secreting the pancreatic juices. And then, after being digested into simple fatty acids with the help of bile and with the help of the pancreatic amylase lipase, a further breakdown occurs in our starches, in our fats, and to some extent our proteins. And then the food makes its way into our small intestines, where the microflora and the bacteria play such a big role, along with other mechanisms like the rich supply of neurons in the whole lining of our gut, the migratory neuronal plexus, as well as other hormones like gastrin and secretin and cholecystokinin. So these play such a dynamic role in the whole digestive process. And all of us here know the importance of gut health, gut bacteria. But how does this play a role when it comes to our hormones, especially hormones like estrogen? We're going to talk more about that. So let's talk about what is the enterobiliary hepatic circulation. So this involves substances that are metabolized in the liver, excreted into the bile, and then passed along into the intestinal lumen, where they then get reabsorbed across the lining of the intestinal mucosa, and then return back into the liver through the portal circulation. So this is a very complex system, but it plays a massive role when it comes to toxins, and especially toxins that are fat soluble. And when we are dealing with what are called xenobiotics and xenoestrogens, that I'm going to cover in more depth. And then, of course, I'll be talking more about the role that the intestinal bacteria play in this entire enterohepatic biliary circulation, and how drugs, common drugs like antibiotics, how they can block this process and result in problems. So this is a schematic view of how this works. So when we eat our food, then it is acted on by the bile, which is made in the liver and then secreted through the gallbladder into the second part of the intestine, known as the duodenum. And once it is digested, then and reabsorbed, then through the portal blood, it is pumped back into the liver, into the bloodstream, and then back into the right side of the heart, where blood is oxygenated and purified and transmitted to the rest of the system. But the portal vein carries the nutrients into the liver. And so the bile acid synthesis occurs normally in the teeny tiny canaliculi that line the liver, and this is known as the de novo synthesis of bile acids. And the backbone of the bile acid is always cholesterol, and that's why cholesterol plays such a big role in bile acid synthesis. And like everything else in our body, we want this Goldilocks phenomena, not too much, not too little, and that goes the same when it comes to our cholesterol. So these bile acids are synthesized in the liver cells, also known as the hepatocytes. And then these, once they get synthesized, they combine with amino acids to become something known as cholic acid or chenodeoxycholic acid, which are the main primary biliary acids, bile salts. And then these get conjugated with glycine, which is the main amino acid in humans. There are other amino acids in rodents like mice. The bile acid is then transported along the bile canaliculi and stored along with the cholesterol and phospholipids in the gallbladder. And when we eat food, that then the partially digested food that enters from the stomach into the duodenum sets off the trigger that stimulates bile production and bile flow, which further helps in the digestion of fats and proteins, and also facilitates the emptying of the stomach and prevents what is called lazy bowel or gastroparesis or slow gut motility and problems of such nature. And then this is the simple view of how complex this whole structure is and how bile acid is synthesized. So in the liver, we have these sinusoids, and they consist of a kind of central hepatic vein. And then this is drained off into, there are the veins, arteries, and the bile ducts, which kind of at the microscopic level then branch off and then you reunite to form ultimately the portal vein, the common bile duct, as well as the portal artery. And so these are known as the portal triad. And whenever there's anything seriously wrong with the liver, it can impact the function of the portal, the entire portal system, causing things like cirrhosis, portal hypertension, and jaundice. And so this is another schematic view of how the portal vein and the bile acids play a role in this recirculation between the gallbladder, the liver, the intestine, and the portal vein. And then part of it then enters a systemic circulation. So when bile acids pass through the intestinal tract, they contribute to absorption of important nutrients like your fat-soluble vitamins, which is vitamin A, D, E, and K. And that's why eating good fats is such an important part of our diet. And then in the intestines themselves, the gut microbiota play the biggest role in deconjugation and dehydroxylation of the primary bile acids, converting them into secondary bile acids, enhancing the diversity of the bile acid pool. And then in the jejunum and the colon, the unconjugated and uncharged bile acids enter by a process known as passive diffusion across the cell membrane of the enterocytes. And then this enters into this whole circulation. So in the small bowel itself, the active uptake of these conjugated bile acids takes place through the apex, the apical sodium-dependent bile acid transporter, also in short known as ASPT. So in total, about 95% of bile acids are reabsorbed into the intestinal cells, and then the remaining 5% is excreted in the feces via the bowels, and then this loss is compensated by new production of de novo bile synthesis in the liver, which is the primary synthesis of bile. So this is the whole enterohepatic circulation. And there are specific transporters within the cells or the enterocytes, which make sure that bile acids are redirected to the liver via the portal vein. And about 90% of bile acids are cleared from the hepatics circulation for reuse, which is pretty amazing. The bile acids can be recycled up to 4 to 12 times per day between the hepatocytes in the liver and the enterocytes in the intestines. So this constitutes the enterohepatic circulation, and only a small percent, which is less than 10%, really reaches the systemic circulation. So this systemic plasma bile acid concentration, when you measure it, it will show a slight rise just after a meal, and it shows a daily rhythm based on the timing of our food intake. In addition, hepatocytes are also equipped with specific mechanism to promote bile acid excretion when hepatic bile acid concentration increases, which can be due to a number of factors, including stress, medication, surgery, blockage, all of those. And so really these bile acids have a detergent-like function, and they can be toxic if they accumulate. So when there's liver damage or liver failure, that's why you get a high level of plasma bile acids, because that whole equilibrium is disturbed and we end up with jaundice. So, and you may have heard of the drug cholestyramine, which is a very well-known and old medication, which was initially used to lower cholesterol. And it totally utilizes this whole enterohepatic biliary circulation mechanism to perform its function. So in the intestine, the bile acids are transported, as you know, to diffuse across the enterocytes lining the intestine to the basal membrane, and then excreted into the portal blood for circulation back into the hepatocyte sinusoids. Now, this pathway was first exploited to kind of lower high cholesterol levels. Why? Because we know that bile acids are made up with a backbone of cholesterol. And what cholestyramine does is it acts as a positively charged resin or a sequestrant that binds to negatively charged bile acids so that they are not transported back to the body, but eliminated in the feces. But we can use the exact same mechanism to also utilize this function of cholestyramine to get rid of toxins like mold and Lyme and some of these biofilms that could be sequestered within our GI system, especially say after a cholecystectomy, or like gallbladder surgery or even bowel surgery. So as more bile acids are removed, less are reabsorbed, thus lowering hepatic bile acid levels and in turn lowering the cholesterol levels because of this mechanism. So the other situation when this is impacted is when someone has had a cholecystectomy or surgery to remove the gallbladder. You know, this is a common process involved to treat symptomatic gallbladder disease. However, we know that the gallbladder plays such an important role in this whole metabolic process. So this event can have metabolic consequences. So the mechanism, what happens is that because the gallbladder has been transected, the bile acid flow is impacted, as well as the rhythmic contractions of the gallbladder in the fasted and fed states. So as a result, what happens is the small intestines alone have to act as the bile acid pump to regulate the dynamics of this enterohepatic circulation of bile acids. And this can lead to a more rapid transit of the bile acid pool in fasted cholecystemized patients. So what are some other factors that can impact our biliary enterohepatic circulation? Diet plays a big role, especially fats and fiber. So it's so important to eat lots of good fiber and good fats in our diet, but avoid the bad fats like your margarine and the omega-6s, refined oils. The colon transit time affects GI motility, as you know, drugs, the gut microbiome, the gallbladder functional and motility, and any surgical intervention. The liver also plays a huge role in detoxification reactions. So no matter what we put onto or into our body in the form of toxins, foods, drugs, lotions, whether we inhale it, a large part of it then enters the circulation or through the gut, it goes to the liver. And in the liver, we also are able to do part of the blood sugar management. And this can be affected by factors like stress, diet, inflammation, as well as things like insulin resistance, fatty liver, and cardiometabolic disease. And so the liver is also where we store fat soluble vitamins like A, D, E, and K, as well as minerals. So the liver plays a great role in detoxification, in metabolism, but also it impacts our immune system. So the liver and fats, how are they related? The liver helps us maintain a healthy cholesterol level, and this is needed to even balance our hormones, especially what I call the steroid hormones, which are estrogen, progesterone, testosterone, and even cortisol. But the liver and the gut also play a role in conversion of T4 to T3, which is the inactive thyroid to the active form, with the help of supportive micronutrients. So the liver not only produces bile, but bile itself then plays a role in the absorption of fats. And so abnormalities in the liver function in turn influence hormone imbalances and digestion. So what are the two main pathways in the liver that help in detoxification? So we have phase 1 and phase 2 detoxification reactions, and the liver is equipped with these myriad of enzymes which are supported by the gene that codes for that particular enzyme, which then leads to the process of hydroxylation, mainly in phase 1 with the P450 enzyme system. And then in the phase 2 detox reactions, which are mainly mediated by enzymes like the UDP glucuronyl transferase, the glutathione S transferase, the amino acid transferase, the N-acetyl transferase, and methyl transferase. And these main blocks of reactions are conjugation and glucuronidation. So and the genetic variations in the CYP1A1 and CYP1B1 system can impact how we even break down our hormones, especially estrogen, into its metabolites, which include 4-hydroxyestradiol, but there are others like 2-hydroxy and 16-hydroxyestradiol. And we'll be talking more about how free radicals can play a big role when it comes to the cellular damage that can occur as a result of the type of estrogen metabolite that is produced predominantly, and then how that can impact even risk for things like breast cancer.
Ты мне что-то сделал?